That's what I told Dontavius. I told him. Now I got him on record. Okay. He sits right here. He's a little out of control. So he's a good-natured kid. So we're going to do a little bit of this. It's not really much to it. Probably take us about 5 or 10 minutes, and then I'll give you time to work on the homework. We'll do another one of these time things at the end. Right? That'll be the sum total. Should be out of here without any homework for the weekend. Watch the Super Bowl. If you want, we can talk about the deflated football. What's that? I got a feeling Seattle wins. Yeah. I don't really follow it much anymore, I have to say. I used to follow all sports really close. Okay. Thank you. Okay, again, this is kind of baby stuff, but we've talked about squaring, right? The opposite or the inverse of squaring is square roots. Okay, so let's see. The square root of 81. Oh, before I start that, I wanted to hand out these are formula sheets. On the back, on the front, it's got the algebra 2, but on the back, it's actually got all the multiplication tables, all the perfect squares, all the perfect cubes. Not all, but a fair number. So they're in document protectors because I do want them back. But I can. Cuatro. 2, 3. There you go. So this, you could see on where you see the perfect squares, you could see that 81 is the perfect square, right? I mean, this is a multiplication table anyways, right? That's in the square root of 81 would be 9. Okay, quiet please. Andre. The square root of 81 is 9. Okay? Now, if you were in Algebra 2, you probably have seen it where sometimes they say plus or minus 9. But this is not a case to say that. When you're given a square root, the symbol is there. You assume they mean the positive and not both. It's when you're solving an equation, that's when you stick the plus or minus. We're not interested in that right now. Okay, so let's see. Okay, how about that one? The square root of 64, because 8 squared equals 64, then the square root is 8. 8. And the square root of 25, right? 5 squared is 25, so the square root is, undo. No, I don't think so. Okay. 5. Okay, so try. Now, what if it's a fraction that's inside? But in this case, you could see that both the numerator and denominator, they're perfect squares. Got pass? Okay. Thank you. So when you're taking the square root of 9 over 16, you know what the square root of 9 is? 3. The square root of 16, 4. So the answer is 3/4. Okay, what about the square root of 1 over 36? That equals 1/6, right? The square root of 1 is 1. The square root of 36 is 6. Okay, how about? Okay, so just look at individually the square root of 81, which we've already done, is 9. The square root of 11 is, or 121 is 11. Right, so simple stuff. It does require, if you're going to do it without a calculator, that you know the perfect squares. You got to recognize them. I mean, so much of what we do in Algebra 2, for example, depends on a recognition of, for example, when you do a difference of squares, if you don't recognize that number as a perfect square, you wouldn't think to solve it that way. So you got to know those. Okay. concept. Numbers, sets of numbers. Up till right now, we're interested in what we're calling real numbers. Real numbers are things in the physical world that you would graph, right? If you're putting things on a graph, it's a real number. The basic sets of numbers start with natural numbers. I know that's a little hard to see, but natural numbers are counting numbers, right? Starts with 1 and goes up from there. What's the difference between a natural number and a whole number? There's a 0. With whole numbers, you start with 0, not with 1. So that's why the only thing they've got written there is that there's a 0 that's in this set that was not in this set, right? Integers are negative, -3, -2, -1, 0, 1, 2, 3, right? It goes infinitely positive, infinitely negative. It's the whole numbers plus and minus. That's what we mean by an integer. Now, if you look at their examples of integers here, -10/5 doesn't look like it's an integer. But if it can be simplified to be an integer, then it's an integer. So 10/5 is 2, that's -2. The square root of -16. Okay, that simplifies because 16 is a perfect square. So that is an integer. Okay, we got to remember that rational numbers mean any number that can be written as a fraction. Even if it's not written as a fraction, it can be written as a fraction, which is why inside of the big block here that has rational numbers, you've got integers, whole numbers, and natural numbers, because you can always turn one of them into an integer by or into a fraction by putting it over 1, right? -3/1. Okay, now it's a fraction. So everything can be turned into a fraction by putting it over 1. Now, that definitely looks like a fraction. As decimals, as long as the decimal either 1 terminates, means it doesn't go on forever, or 2, it doesn't repeat itself, or it repeats itself, then it can be a rational number. 0.3 with a bar, that means 3, 3, 3, 3, 3 forever. That is a fraction. That's 1/3. So as long as it can be written as a fraction, it's a rational number. The square root of 0.25 is, oh, sorry, that's wrong, 0.5. So simplify it, now it's a decimal. It's a terminating decimal. What does 0.5 equal as a fraction? It's a half, right? So that's a fraction. Looking at the decimal, you could say, well, that's 5/10, because it's one place to the right, or 1/2. Okay, now, if a number as a decimal does not terminate, like it's got ... at the end, and it doesn't have a pattern that's repeating itself, then it's irrational, right? Then it's not a rational number. It can't be written as a fraction. Normally, the numbers that we look at that we call irrational are either they're going to show you a decimal like that, which clearly doesn't have a pattern, and because of the ... it doesn't stop. Or they're going to give you a square root of something which is not a perfect square. Okay, that would be irrational, an unresolvable square root, which is the same reason why the square root of 123 is the irrational number, right? 123 is not a perfect square. Or pi. Pi is an irrational number, because what do we know about pi? It goes on forever and it never repeats itself. 3.14156 ... forever. So which of the sets will we put 15? Let's just think of the simplest set of numbers, not every set. 15, would you call that natural, whole, integer, rational, irrational? Yeah, I mean, it would definitely be here. But if it's here, it is technically a whole number and an integer and a rational number, right? It is in all those sets, but let's just say natural numbers is where it starts. And see, they included all of them there, but let's just stick with that. What about -1.4583? Stop. It's a decimal, but it stops. It's rational. does not stop. And the square root of 57. Is 57 a perfect square? No. So it's like one of these here. It's an unresolvable square root. So that would be irrational. Okay, easy stuff. Okay, so how about this? The square root of 9. So what set does that fall in? I mean, you could put it all the way inside the natural, right? I'll say that n for natural. And 3 over 10. 3 over 10, it's a fraction. Rational, right? Negative 0.45. Rational. Decimal, but it does stop. And the square root of 12. Okay, that's like 12 is not a perfect square, so it's irrational. You know, besides all the sets of numbers, most of this doesn't make too much difference, except for 2 of them that you get asked. I mean, if you take the SAT sometime, the questions are just going to say things like, what is the integer that? And then they go on and they explain something. But if you don't know what they mean by integer, if you're getting stumped with that word, then you're in trouble. And I would say that's the same thing about rational and integers. Those 2 words, when they get used, you kind of need to know what they're talking about there, right? I don't think most of us deal with natural whole numbers as sets of numbers anymore. That's kind of like way back when. You know, irrational is okay, but I think that in terms of reading a question on the SAT, integer, rational number, you got to know what those words mean. Okay, then the properties of real numbers. And I think that you've probably seen these properties for years, and it doesn't matter how many times you see them, you still struggle sometimes to name the property. It's less important to know the name of the property than it is just what does the property say. For example, in commutative property, it just means the order is not important. You know, do you know instinctively that 2 plus 3 equals 3 plus 2? Okay, then you're using a commutative property. Okay, whether you know the name commutative property doesn't make a lot of difference. What's important that you know that you could switch the order without changing the value. That's good. You know, so the ones that we use mostly are commutative property, order. Associative property means grouping, if you just change the parentheses. An identity property, there's 2, right? One for addition and one for multiplication. You know, if you add anything to plus 0, you get that same thing back again. So you would say that 0 is the identity element for addition. For multiplication, it's 1, right? Anything times 1 equals the same thing back again. It's identical to what you started with. An inverse property is, you know, what do you do when you're adding to get you back to the identity element? So since 0 is the identity element for addition, what do you add to A to get 0? Well, you add the opposite, right? Any number minus itself is 0. This one is not a great example. I mean, this is the inverse for multiplication. A times 1 over A is 1. It would look better to me, because where we usually see this is like when we're solving a problem. Let's say it said 2/3 x equals 9. How do you solve for the x? And the truth is, you multiply by the inverse being 3/2. Right? This doesn't give you the flavor of the fraction part of that. Maybe if it said instead, A times B over A equals 1. Anytime you multiply a fraction by its reciprocal, you get 1. And that's why if you're solving a problem like that, you would multiply by 3/2. Because of that property there. Now, to me, the most important properties, and this one is by far the one that we use the most, is the 0 property of multiplication. Meaning, what is 0 times anything? It's 0, right? I mean, we use that in algebra when we're factoring, where we're solving by factoring. When we factor and it's all set equal to 0, we know that if a product equals 0, it's got to be because of one of the factors equals 0. So we use this property whenever we're doing factoring to solve equations. That's what we're doing. It's this property right here. And that is an important property. So 0 times anything is that same thing back again. And this one is not a bad property. Multiplication property of -1 just means if you multiply anything by -1, you get the opposite. And I find a lot of times that, let's say you were solving an equation and you had -x equals 23. Oh, I didn't even write that. Equals 23. And you still had to solve for the x because that's not x, that's -x. How do you solve for x? A lot of times students will say, divide by -1. Technically not wrong, you get it right. But generally, you're using this property and just multiply both sides by -1, right? That will turn a -x into a positive x, right? It's not really dividing by -1, but it has the same effect. Okay, so which property is this first one? 42 times 0 equals 0. 0 property. 0 property of multiplication. Okay, what about this one? What's changing between the left side and the right side? The parentheses. Which property is associative? Just think associate group, you know. That's an associative for addition. How about 10x plus 0 equals 10x? Identity for addition. Good. Boom. We're almost done. Which property? 4x times 1 equals 4x. All right. Why is that not wanted to go? Right. Identity for multiplication. How about the next one? Now look closely. What's changing from the left to the right? Did they move the parentheses? No. What did they change? It's an order, right? They changed the order of what was in the parentheses. Well, which property says order doesn't matter? Commutative. So that's commutative for addition. Okay. And that was it. And that's the homework.